Ok, adelante.
Is everyone back? Yes? I don't know.
Yes.
Okay. Okay, one yes, I go. Okay, so let's start the second course. So we will really get into the PISCES parameterization with this second course. Okay, some information about the PISCES code. So it is based on there is one publication that is the reference publication for now about this code. It's the Aumont et al. Paper. I think I will give you, or I can give you the reference in the chat later, which describes. So this paper is very good because it describes really in detail all the equations that are in the PISCES v2 version. The PISCES v2 is really the version that you will be using in the practical course. So it is a scientific paper. This publication, it's not really a documentation that describes the code. So there is really difference between a publication and a documentation. And unfortunately, there is no documentation available. There is a plan to produce one, but it's not available yet. So that's a bit of the difficulty with this code. So PISCES, the PISCES model is coupled. Initially, historically, it was coupled with first with the NEMO ocean model. So maybe some of you have heard of this model. It's more often used in the global, or at least at basin scale. And in 2006, I think it was 2005, 2006, it was coupled first with the Ramsagriff version, and now it is also coupled with the CROCO model. For those who don't know, Ramsagriff is the previous version of CROCO. There are differences, but the old version is Ramsagriff. Okay, so now in the course, I will not detail all the model because it's really impossible in 1 hour. So I will give only some information about the most important processes, in my opinion. So that's it's not an objective choice; it's more a personal choice. So if you want to know more about other aspects, I mean, you will have to dig into the publication, the Aumont et al. Publication, but also there are many publications using PISCES. So if you want to have some more details about other aspects that I do not describe here. So depending on the CROCO version, so I'm assuming that all of you are using or plan to use CROCO or have used in the past maybe Ramsagriff. So depending on the CROCO or Ramsagriff version that you have used, you might have PISCES v01 or PISCES v2. Now, PISCES v0, at the level of detail that I'm going to give today, it's not very important to describe the differences. But there are differences. And what I'm going to describe today are like common parameterization in PISCES 0 and PISCES v2. And then at the end of this hour, I will give a brief overview of the new potentialities of PISCES v2. So in the equations that I will describe in the following slides, there may be some small differences with the parameterization that you will see in the paper, but the philosophy is really the same. So maybe it's not going to be exactly the same notation, etc., but it will be really, really close. Okay, so I'm starting now. So first here is a general sketch of the PISCES model structure. So you have 4 big compartments: nutrients, phytoplankton, zooplankton, and dissolved organic matter. In fact, you have 5 because here also you have particulate organic matter. So it's a little bit, as I said in the previous course, these different compartments, they interact. And now, in this diagram, the squares are the stocks. They represent stocks of matter. And the arrows here, they represent fluxes of matter between the compartments. Okay. So if we start with the nutrients, in PISCES, what is different from this model with, sorry, I made the wrong click. What is different with this model from other models is that the PISCES has a lot of different nutrients. So it has nitrogen in two different forms, nitrate and also ammonium. It has phosphate, it has silicate, and it has iron. So originally, what is really difficult and complex in PISCES is the iron cycle. I'm not going to describe that because I don't think I could be able to really describe that in really detail. But this is really, originally, Olivier Aumont worked on the iron cycle a lot. So there is a lot of details in the iron cycle. Where there is less detail and maybe less processes is on the nitrogen cycle. For instance, there is no nitrite. You know that nitrite is a species, a chemical species that you can find in oxygen minimum zone due to denitrification. So we don't explicitly denitrification and nitrite production is not explicitly modeled in PISCES. So there is maybe not a lot of detail on the nitrogen cycle. Also, what is represented is the carbon cycle. Okay, so I'm going to that. So here you have like inorganic nutrients, and when they are incorporated in phytoplankton, phytoplankton is described, the matter of phytoplankton is described in different ways. It is described as a concentration of iron in the phytoplankton, also the concentration of silicate in the phytoplankton, and the concentration of chlorophyll in the phytoplankton. So phytoplankton is not just one big box of carbon, but it's also a certain quantity of iron, silicate, and chlorophyll. So that's important. That's why you have this C here and Fe, silicate, chlorophyll. As you can see here in the phytoplankton, we have these two boxes. These two boxes, they separate two sizes of phytoplankton. The small ones, which is called the nano phytoplankton here, and the big ones, which is called, in fact, the diatoms. And you can see the difference between the two is that nanophytoplankton, when they grow, they need iron and they need iron. And also, of course, they produce, in their cells, they have chlorophyll. But diatoms, they also need silicate. So that's the difference. There's a big need for silicate. And sometimes when there is not enough silicate, there is limitation of diatoms. Okay, so this arrow here from nutrients to phytoplankton is photosynthesis. Then phytoplankton is linked to, for instance, zooplankton. Why is that? Because zooplankton is grazing on phytoplankton. And as you have two sizes of phytoplankton, you have the corresponding, well, more or less corresponding microzooplankton and mesozooplankton. So the small zooplankton and the big zooplankton. As we will see later, the small zooplankton eats phytoplankton from the both sides, but the mesozooplankton eats from the both sides, but also eats some microzooplankton. So there is, in fact, an arrow between the two. But this is a different compartment of zooplankton. Phytoplankton has different arrows that go away from it one that goes directly to the particulate organic matter. So this is, for instance, when the phytoplankton dies, when there is a mortality, or when it is consumed by a fish, for instance. This is not explicitly parameterized, but it goes in this arrow here. You can have a flux of matter directly to the particulate organic matter. When the phytoplankton produces exudates, so when it eats, when it's producing its matter, it also loses some carbon through exudation. And this is the arrow here from phytoplankton to this DOM, which is the dissolved organic matter. Okay. Then zooplankton, when they grow, so they eat phytoplankton. They produce excretion and exudation, so they produce directly nutrients, and in particular, they produce ammonium. But also, they produce fecal pellets, which are produce a flux to the particulate organic matter. Okay. And if you look now at this particulate organic matter, here you have again two sizes. The small with a small s, it's small particulate organic matter, and big particulate organic matter. And also in this particulate organic matter, different elements are described: carbon, iron, and silicate. Okay. And then this particulate organic matter here, as I said previously, because it is big, it can feel gravity, so it can sink out of the euphotic layer. So that's why you have these arrows that are going downward, and it can remineralize in the water column, of course, but it can reach the bottom also, and maybe incorporate the sediment if we use a version which has a sediment model, which is not the case at the moment. But so this is really the export of particulate organic matter out of the euphotic layer. Some of this particulate organic matter is remineralized by bacterial activity and is producing dissolved organic matter. And dissolved organic matter is also remineralized into inorganic nutrients. So that's the basic structure of the code. So in fact, all these arrows, there will be terms in the equations. And all these talks will be like the concentrations in the equation. So I will describe not all the equations, but some of them. And we will start with phytoplankton. But first, okay, one thing that is missing, but that is not really coupled with this cycle, is oxygen cycle. So when the oxygen cycle is really important, especially in upwelling regions of Chile and Peru, because you have these oxygen minimum zones. So there is an equation to simulate dissolved oxygen in PISCES. And what happens is that when you have production of phytoplankton, so when this arrow, when there is this positive flux in this direction, you produce oxygen. So you all know that when you have photosynthesis, you produce oxygen. And so this oxygen is a source. So that's why you have this arrow in red. A source of oxygen here due to photosynthesis. When you have zooplankton is consuming oxygen because of respiration. So there is a sink of oxygen. This is this red arrow here. And also when you have a bacterial activity that is remineralizing organic matter, you have a sink of oxygen. These bacteria also need oxygen to do their job, and so they consume oxygen. And the other thing also is that oxygen is exchanged at the interface between the air and the ocean. When you have a warming of the ocean, when the temperature increases, the ocean tends to lose its gas, so it's also losing oxygen. Okay, and when it's getting cold, it can absorb oxygen. So this flux is also represented in PISCES. It's not a biogeochemical flux. In fact, it's a physical flux. It is due to temperature and it is due to the wind also at the surface. And it is due to the difference of oxygen concentration in the atmosphere and in the ocean. Note that in PISCES, the oxygen concentration in the atmosphere is always the same. It's constant. Okay, so there is no variation. But the flux can vary depending on the oxygen concentration in the ocean, in the surface layer, and also on the temperature. Okay, so now we are getting in the core of the code, and we're starting with the nanophytoplankton. So the concentration of nanophytoplankton is called P. This is P here. And this is the evolution equation of nanophytoplankton. So this is the derivative of P. It is due to different terms. You have production here in green, and this is the green arrow. You have a mortality term here in black, and why is it it's a sink. It's a sink of phytoplankton because there is a minus in front of it, so it's a negative. All this will be a negative term. It takes out the phytoplankton, and this is the black curve here. And that black arrow, goes from this green box to the particulate box. And there is also other sink terms due to grazing of zooplankton. So the zooplankton is eating the phytoplankton, so it creates it's a negative term in the equation, which makes this term dp dt decrease. And because nanophytoplankton is eaten by the two zooplankton classes, Z is for the small zoo and big M is for the big zoo. Okay, for mesozooplankton. Okay, so now we are going to detail a little bit all these terms. In particular, production, the first term. So the first term, you can see that it's proportional to the phytoplankton, which makes sense because the growth rate depends on the presence of phytoplankton. If you don't have phytoplankton, you cannot grow. If you have a lot of phytoplankton, if you have some nutrients, you will be able to grow. So there is a proportionality with P. And now you have these coefficients in front of it. First, you can see this coefficient here, 1 minus delta. It's an efficiency coefficient. It means that if delta is 0, you have all this will be produced. But because you have some inefficiency, some loss, delta is not equal to 0. So I will not talk a lot about this delta, but we will focus on this production term, which is mu in Greek, mu nano times P. Okay, first, before we go to this term in detail, we need to look at what matters in photosynthesis. So for photosynthesis, what really matters is nutrients, of course, but also light. So how do we compute the light that is available for photosynthesis in PISCES? In fact, there is an optical model in PISCES that is required to compute the penetration light in the water column. And this model in PISCES is derived for 3 different wavelengths: red, more or less red, green, and blue wavelengths. So for each of these wavelengths, you compute a part of the energy. The par means photosynthetically available radiation. So you compute the par for each wavelength, and the par is computed as followed. Here in this equation, you can see that par at the depth Z depends on the par at the depth z minus dz, so it is at depth closer to the surface, times an exponential coefficient. So this is times dz here. So you see that this dz, this term corresponds to an absorption. And what happens is that this coefficient here, k, is a constant plus something that depends on the chlorophyll amount. So we are back to what we said just before, is that if we have a lot of chlorophyll, this term will be big, so k will be big, and so this term exponential minus k will be strong, will decrease very fast with depth. So we really have a propagation of light in the vertical that depends on the concentration of chlorophyll. And this is, so you have this, the equation is written for the red wavelength, but you have the same kind of equations for the other wavelengths with different constants. And if here there is a schematic of the different wavelengths with a more rapid, in general, more rapid absorption of light in the red, then in the blue, and then in the green. Okay? So this is part of the model, that is the optical model that is needed to have the quantity of energy from the light that is usable for photosynthesis. So now let's look at this term, where this term mu nano is written here. It's separated to one term here, mu p, and a big parenthesis in which we have 1 minus an exponential, and here we can see the par. Okay, so this par will be really important here. This term here in front is a temperature-dependent term with a certain equation. So you probably know that if you have a warmer temperature in biology, the cells tend to divide themselves and to multiply themselves more rapidly. So this mu p increases with temperature. Okay. Here you have the dependency with the par. And you have a third term here, which is really important, which is L lim nano, which is the limitation by nutrient. So you have one term depending on temperature, one term depending on light, and one term depending on the availability of nutrients. Okay. So now let's decompose this L lim nano. As we said before, we have in PISCES several nutrients. So in fact, these limitation terms can be computed for each nutrient in this way. Generally, the nutrient over a coefficient, half saturation constant, plus the nutrient concentration. So you have this for phosphate, you have L nano for iron here, and a little bit more complex for nitrate and for ammonium, with also these constants for each nutrient. And this form of limitation is modeled as this. In fact, it's when you have very little nutrient, it's like there is like the limitation increases with the nutrient, and when you have a lot of nutrient, there is a saturation. When PO4 goes to infinity, this goes to 1. So there is a saturation to 1. Okay, it's called the Michaelis-Menten parameterization of limitation. And what happens is that you can easily imagine that what will matter for the phytoplankton cell is the nutrient that has the stronger limiting coefficient. It means that there is, among these 4 nutrients, there is one nutrient where there is not enough, probably. It is possible that there is enough for all of them, but imagine a situation where there is, for instance, not enough iron, so that this limiting coefficient here for iron will be smaller than all the other ones. That's why this L nano lim is the minimum of these different nutrient limiting coefficients. So it's not an analytical function, it's really the mean. And this allows to determine which one is the limiting nutrient in this situation. Okay, it's not direct. If you want to know which nutrient matters most for the growth here, you have to compute these different parameters to identify which one it is that is limiting the growth. Okay, so this was for nanophytoplankton. It's almost the same for the bigger cells, diatoms. It's almost the same equation here. And for diatoms, the difference is that we have silicate also. So we have all these limiting coefficients as before, not with the same constants, of course, but we add one, which is silicate. So now the minimum is to be taken between the phosphate, iron, nitrogen, and silicate. Okay. Voilà. So with this, I have described almost fully this term of production by photosynthesis, or primary production. Now let's look at mortality. So you can see that the mortality is separated in 2 terms. One term is linear here with a small m, and one term is quadratic because you have mortality for times, the diatoms squared. Sorry, I didn't say, but D is the concentration of diatoms. Okay. And this quadratic mortality is important because it is parameterized here. You can see here this mortality term, and we can see here again this term of limitation. And this means that when there is a nutrient stress, which means that the cells do not have enough nutrients to grow optimally, there can be increased mortality because the cells become sticky, and so they stick to each other, and then they will die and they will sink. So this mortality is dependent on this nutrient stress, which is the value of this limiting term of nutrient. Okay. Okay, I will take some questions maybe at the end. It will be easier, or maybe I will stop. Yes, I will finish the plankton and maybe I will stop for a few minutes to have some questions. Okay, so now let's move to zooplankton. So this is microzooplankton, and I will describe in more detail the different terms. So Z is microzooplankton, and this is the equation. So you have a source term, which is the grazing of phytoplankton, small phytoplankton and diatoms, but also in the version of PISCES, microzooplankton also eats particles. So these are the red arrows. You have microzooplankton here, and it grazes on diatoms, on nanophytoplankton, and on small particles. So this is the source term. This is how it grows. It needs food to grow. Then you have excretion. So excretion is linear with this Michaelis-Menten parameterization again. And then you have also, so you lose matter by excretion. You also lose matter by being eaten by bigger zooplankton. So there is grazing. This is this green arrow. The microzooplankton is grazed by the mesozooplankton. And also there is an additional parameterization which is mortality, quadratic mortality, which simulates in a simple way the grazing by higher trophic levels, like fish, for instance, which are not represented in PISCES. So this is a very simple way to take into account the pressure from higher trophic levels. Now, if we detail a little more this microzooplankton grazing, we have in front of this grazing efficiency. So it's not equal to 1. This grazing efficiency, there are losses. And when you look into detail of at the grazing, you have these grazing parameters, J micro, and J micro here for each species. It can be different. So for instance, for a species N, so if the zooplankton grazes N, you have this complex formula, and this complex formula indicates that there are preferences, which means that the zooplankton prefers to eat, for instance, POC, particulates, and then after he prefers to eat a small phytoplankton, and then after a big zooplankton. Don't take care of this order. I mean, I put it at random, but it's possible to give some preference, some more ways to different stocks of food for the microzooplankton. Okay. And also in this J, there is a dependence on temperature. So when the zooplankton is in warmer temperature, it needs more food. It needs to eat more, okay, to grow at the same pace. Okay, now if we look, it will be relatively similar, but if we look at the big zooplankton, we also have a big grazing term here. It's even bigger than the one for microzooplankton because it grazes on phytoplankton, nanophytoplankton, and diatoms, but it also grazes on microzooplankton, and it grazes on both types of particulates, small particulates and big particulates. So the mesozooplankton eats of everything. Okay, and there is also preferential terms, etc., that are parameterized. And there is loss of matter by excretion, and there is also grazing by higher trophic levels. So it's really very similar. So to detail this grazing preferentials, it's a bit different than the one from microzooplankton, because in fact, you can parameterize, and it is parameterized, so the formulas are a bit complex, but what they mean is that the preferences are not constant, but they depend on what is available. So in fact, the mesozooplankton, in a way you could say it's smarter because it's able to eat more, or in priority, what is mostly available in the system. So if there are more particles, it will eat more particles. And if there are more phytoplankton, it will eat preferentially phytoplankton. Okay, maybe I can take a short break, like take a few questions here. If you have any questions.
Good morning, Vincent.
Yes.
I have a question about the, you are estimated all these variables in terms of biomass or in terms of number of cells for the phytoplankton?
In terms of biomass.
Okay,
so
and you cannot,
yes.
And it's not possible to, because has the phytoplankton cells, they have a time to divide, to duplicate themselves. Yes. It's not possible to modeling that, or is only everything in terms of biomass?
I don't know if it's possible, but Everything is in grams of carbon, in grams of in moles of carbon, in moles of nitrogen, etc. It's not in number of cells. Also because I think it will depend a lot of the species. You cannot, as you said, as you saw, there are only two sizes of phytoplankton, so it's really not realistic because in reality there are many, many different species. So I don't think it would have a lot of sense to separate them in the number of cells.
Yeah.
It's more okay.
Thank you. But I understood now with your response that it's possible to change the biomass chain to use biomass in terms of nitrogen, carbon, and also the another elements, no, silicate and.
Yes, in fact, as you will see, it will be clearer when you do the practical exercise. But for instance, if you look at diatoms, for instance, so you will have not only one variable for diatoms, so you will have several. You will have one mass of carbon in the diatoms. So the unit will be micromoles of carbon per liter. Okay. And you will have also micromoles of silicate per liter in the diatoms, and also micromoles of iron in the diatoms.
Okay.
So
okay.
You see what I mean? There are different elements described in each compartment.
Compartment. Okay.
Yes.
Thank you. Thank you very much.
You're welcome. You're welcome.
Bien, hola. Pablo Córdoba por acá. Voy a hacer la pregunta en castellano. Esto de menos dentro de las ecuaciones el intercambio gaseoso. No sé si eso es otra parte del modelo, está incorporado o no. Quisiera saber sobre eso.
Sorry, no he entendido tu pregunta. Someone can repeat it maybe in English?
Changing of CO2 and oxygen.
No, I didn't get that.
I can replay.
Yes.
He is missing the exchange between the ocean and the atmosphere in the oxygen cycles. He asked if there are some equation about this process.
Yes, of course there are. You refer to this, huh? Yes, of course there are exchanges, but as I said, I don't describe them because it's not biology. In fact, the exchange between the air and the ocean will depend only on the partial pressure of oxygen in the water, which is proportional to the concentration of dissolved oxygen, and the oxygen concentration in the air, which is a constant here. And also it will depend on temperature, and it will depend on the wind. If you have a lot of wind, you will exchange more. So it's not biogeochemistry, it is physics. It's like CO2 exchange. It's not CO2 exchange at the interface. It's not biogeochemistry, it is physics. What is not physics is how the concentration of oxygen is set in the surface layer. But the exchange with the atmosphere is just a physical process. I don't know if I'm clear. But yes, it is described, and if you look into the code, you will find a routine where you have all the information to see how this is parameterized.
Okay, thanks.
Okay, so maybe I continue. I think I'm already at 40 minutes, so I will go on for another like 10 minutes, and we will have a break. Okay. I was there. Yes, I was there. So we are done with phytoplankton and zooplankton. And now we are going to describe the dissolved organic matter or dissolved organic carbon equation. So it will be easier now because we have described some of the elements, the key elements for phyto and for zoo. And in fact, you will recognize that some terms are coming from these phyto and zoo expressions. So for instance, here you have a source term of dissolved organic carbon, which is due to this efficiency term of primary production. So you have this lambda coefficient. So what is not produced in the primary production, a part is not really transformed into organic matter. A part is lost to dissolved organic carbon. And this is this part, organic exudation by phyto. Also, you have this excretion term. So excretion, I'm not sure it's clear to everyone, but to me, it's kind of a difficult to compare, but kind of a sweating or peeing of the zooplankton. So it's losing some dissolved organic matter, and this is the excretion term. And also, as I told you, there is some inefficiency also of grazing. So part of this grazing here, you can recognize with G, P, all these J's are grazing. So you have something that is proportional to the grazing, and that is producing dissolved organic matter. This is organic exudation. Okay, so these are all source terms. Another source term is the degradation of a small particulate organic carbon. So you have very small particles that are getting so small that they are counted as dissolved. They don't fall anymore. So you have a flux with this coefficient that is important for determining this flux. So all these terms are sources, but then you have these sink terms that are with minus in front. Here you have a minus lambda doc. So if you have a lot of doc, you have a constant rate of remineralization, and it's a flux of towards ammonium and dissolved organic carbon. And also you have a loss of dissolved organic carbon that goes to the particulate. So dissolved is really being fed by the particulate here by degradation, but also it can be stuck with particles, and so it can aggregate with the particulate organic carbon. And so I will describe just briefly this aggregation. It's easy to understand. It's more now it's not really biogeochemistry. It's more like chemistry or maybe statistical physics. But what you have is a flux from dissolved organic carbon to small particulate organic matter. And this is proportional to the doc squared. So when doc meets another doc, they get bigger and they can become POC small. And also when a doc here meets a falling POC, then it's a lost term, it gets a bigger POC. Okay, so these fluxes just say that these molecules, they bump into falling bigger particles and they get aggregated. Okay, and so you have a parameter that comes into play here, which is SH, and it's an effect of turbulence. So this term is really small, really high in the mixed layer, and really small below the mixed layer. And you understand this, if the particles are moved a lot by strong mixing in the mixed layer, they have a higher probability to encounter and to become POC. Okay, now I'm going to POC. So small POC results from different things. Again, the grazing. part of the grazing, when they graze the zooplankton, they don't ingest everything. They spit out some of the food that they try to eat, so they produce some detritus. There is also a production of calcite shells, because you count a proportion of the small phytoplankton is counted as calcifying phytoplankton. Also, you have the term that is due to mortality. You have mortality of phytoplankton. Of diatoms here, you have mortality of zooplankton. So these dead corpses, dead algae or dead zooplankton, they produce particles. So these are the three source terms, sorry. And then you have some sink terms, again. Some degradation of smallpox into DOM, as we just saw. That's why there is a minus here. And also some sinking. So here it's interesting because it's a different equation than the others. For the first time here, you can see this dPoc dz. So that's the vertical gradient of POC. So it's really like an advection equation, advection term, due to the vertical velocity, which is a sinking velocity here. Okay. So this term here means that there is sinking of the small particles towards the bottom. And then you have the aggregation terms that I described just before. Okay, and that's what I wrote down there, is that, yes, this term is exactly like the vertical advection term of a dissolved tracer when you have minus W dc partial z, where W is the vertical velocity of the fluid. Here, W is not the vertical velocity of the fluid, it is the sinking velocity of the particle. Yes, and this sinking velocity is not constant. Why is it not constant? Because we kind of mimic the fact that when you go at greater depths, the particles tend to aggregate more and they become heavier. So you have, in fact, bigger particles in this compartment, and so you increase the sinking velocity like this. It is a little bit that is what is schematized here on the right side, and you have a formula to increase the velocity. Okay, so a lot of small-scale effects are in fact parameterized. Okay, and I will not describe the big POC because it's almost the same. So maybe I will skip this one and I will go a little bit to oxygen. And oxygen equation. Okay, just wait a second. Okay, maybe we'll stop here for the break. And I will come back. I will start again with the oxygen equation. Okay?
Okay.
Okay.
Okay, everyone? Yes, I will stop there. So we take a short break.
Ok. Voy a cortar la transmisión y